Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 9, Lesson 4 on square root arithmetic. So one of the things that you are required to learn in Algebra 1 is a little bit about what you can do with square roots in terms of adding, subtracting, multiplying, dividing, things like that. So let's get right into the different types of arithmetic that we can do with square roots. And let's begin with the multiplication property of square roots, which we saw a few lessons ago. Now, there are times when you will need to be able to do some basic operations involving square roots. We've already seen some of this with the multiplication property of square roots, and recall what that property was, right? And it was pretty simple. Square roots play real nice when it comes to multiplication and division. In other words, if I have the square root of a times the square root of b, I can get the square root of a times b. And likewise, I can reverse that. If I have the square root of a product, I can do the square root of each portion of the product and then do the product, right? So we've done exercises like this before. Let's take a look at exercise 1. Find each product below. Write each answer in simplest radical form. All right. Now, I will say for the record, when we did these types of problems a few lessons ago, when we multiplied them together, what happened was we always got a nice perfect square underneath, okay? Here, we're going to be using that multiplication product that I've now property that I've now moved off the screen. We're going to use it twice. So let's take a look at letter A, where we have the square root of 8 times the square root of 5. So the first part of the multiplication property of square roots says, well, I can make that into the square root of 8 times 5, which is the square root of 40. Now that's perfectly good, but it's not in simplest radical form. To write it in simplest radical form, I need to find the biggest perfect square that divides into the radicand. That's the number underneath the square root, right? And the biggest perfect square that goes into 40 is actually 4. So I can rewrite the square root of 40 as the square root of 4 times the square root of 10. I take the square root of 4, that's 2. I leave the square root of 10 alone, and I get 2 times the square root of 10. So square root of 8 times square root of 5 is 2 times the square root of 10. All right, what I'd like you to do is try to do the same procedure in letter B and letter C and see what you get. All right, well, letter B, very similar to letter A, maybe even a little bit too similar to letter A, right? That's going to be the square root of 6 times 15, which is the square root of 90. Then I'm looking for the biggest perfect square that goes into 90. That happens to be 9. So I can make this into the square root of 9 times the square root of 10. And that's going to give me 3 times the square root of 10. I really like, apparently, the square root of 10 in this particular problem, including letter C, where we have the square root of 10 times the square root of 10. Now in this one, what's interesting is when you do the square root of 10 times the square root of 10, right, you get the square root of 10 times 10, which is the square root of 100, and that's equal to 10, right? I can definitely simplify that radical because 100 is a perfect square. Now letter C is extremely important. It's probably the most important problem in exercise 1. Notice square root of 10 times square root of 10 is the square root of 10 squared, which is just 10. That is no great shock, and it's extremely important, right? There's a major consequence of the multiplication property of square roots that you must feel comfortable with. Let's take a look at that in exercise number 2. Write each of the following products in simplest form. Well, you're probably going to notice a pattern pretty quickly here, right? You know, if I've got the square root of 5 times the square root of 5, that's equal to the square root of 25, and that's equal to 5, right? Why don't you see if you can finish the remaining 3? Pause the video now and go ahead. All right, well, the square root of 8 times the square root of 8 is going to be the square root of 64, and that's just 8. The square root of 11 times the square root of 11 is the square root of 121, and that's just 11. And the square root of a times the square root of a will be the square root of a squared, and that will just be a, right? And this is so amazingly important. Whenever you multiply a square root by itself, you just get the radicand back. And that makes sense because we're squaring a square root. They're just undoing each other, right? So if I square the square root of 5, I get 5. If I square the square root of 8, I get 8. Square the square root of 11, I get 11, etc. And that is amazingly important. All right, we're going to see why that is in a moment when we learn how to rationalize a denominator containing a square root. Now, this is similar to simplifying a square root. For historical reasons, a fraction is not considered simplified if there is a square root in the denominator. That's the bottom of the fraction. In the numerator, go ahead, no problem. But for some reason, fractions in the past used to not be considered simplified if they had a square root hanging out in the bottom of the fraction, kind of like 2 over square root of 3. We can use properties of fractions and square roots to rewrite these types of fractions so they have a rational number in their denominator, which is why this procedure is called rationalizing a denominator. Okay? We're trying to make the denominator, the number in the bottom of the fraction, typically we want to make it into a whole number, but a whole number is a rational number. All right, so let's see how that is done in exercise number 3. It's actually pretty simple. Let's take a look. Consider the fraction 2 divided by the square root of 3, which has an irrational denominator. Using your calculator, write the value of this fraction using every decimal possible. All right, great. So take your calculator out, do 2 divided by the square root of 3, and see what you get. Pause the video now. All right, well, I need to break out of here just for a second. Open up my calculator. Now we had 2 divided by the square root of 3, and we get this messy long decimal, right? 1.1547, etc., etc., etc. Okay, so let me just, so that I can actually write this down. Yeah, I'm going to put it right there. I'm going to have 1.154700538338. All right, great. Let's go back to full screen. We'll leave our calculator kind of hanging out down here. Letter B, simple enough. Does the fraction appear to be a rational or an irrational number? Well, certainly at the end it almost appears like we have some repetition going on, but remember we need this like overall repetition of the pattern, and that certainly doesn't seem to be happening here, so this appears like it's an irrational number. And side note, it is. All right, now let's take a look at letter C. All right, this is very important. Find the following product. 2 divided by the square root of 3 times square root of 3 divided by square root of 3 in simplest form. Then find its decimal value. All right, well, let's take a look. Let's do this one together, okay? So all I'm asking you to do in this case is multiply 2 fractions. Now, when we multiply 2 fractions, always, 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 when we multiply 2 fractions, I multiply the tops, I multiply the bottoms. I know it would probably be tempting to sort of like cross cancel here. Don't do that. I have 2 times the square root of 3 in the numerator, and square root of 3 times square root of 3, which we figured out just a moment ago, is equal to 3 in the denominator, right? Root 3 times root 3 is equal to 3. And 2 times square root of 3, I just literally wrote back down as 2 times the square root of 3. That's all I did. Now it says find its decimal value. So take a moment and actually figure out what the decimal value of 2 times the square root of 3 over 3 is. Take a moment to do that on your calculator. All right, well again, I'm going to break out of the program just for a moment because I want to put this calculator on sort of a larger version, although I need to make it small enough to get it up there. Okay, here we go. So I'm going to use my fraction bar this time. Remember, I had 2 times the square root of 3 all over 3, right? So the result of that problem was 2 times the square root of 3 over 3. I hit enter, and notice, right, I have exactly the same decimal here as what I did to begin. So when I took 2 over the square root of 3, and I multiplied it by square root of 3 over the square root of 3, I got exactly the same decimal. Exactly the same decimal. So let's let's get that in there. Right? That was 1.15470053838. Right? Whoops. Well, that's fascinating and worrisome. All right. Somehow there's two calculators there. Okay, letter D. Why is the fraction in C equivalent to the original one? Right? So why did this calculation give us something that was identical to this calculation? And please note, right, this fraction now has a number in the denominator, the number 3, which is a rational number. But really, that's not what I'm asking about here. Why are those two equivalent? Pause the video now and see if you can figure that out. Oh, well, it's really simple. It's all about this fraction, right? The square root of 3 divided by the square root of 3 is equal to the number 1. And whenever we multiply by 1, it doesn't change anything. Right? So the idea here is, I take this fraction, 2 over the square root of 3, and I want it to have a rational denominator. So what I end up doing is I end up multiplying it by the number 1, i.e. the square root of 3 divided by the square root of 3, right, in a way that makes that denominator a rational number. Now again, you might very reasonably say to yourself, why would I ever want to do this? What good would this ever be? And this is one of those few times in math when I'd have to say, yeah, I don't know. Again, kind of like for historical reasons, there are reasons why we wanted to keep irrational numbers out of the denominator. Those reasons really aren't relevant anymore because we have calculator technology. But it's still a topic that is in standards and will show up on standardized exams. I'm just sorry you have to waste your time learning it. All right? Now, you can turn a fraction with an irrational denominator into one with a rational denominator by multiplying by the number 1 in an appropriate form. So let's play around with that a little bit in exercise number 4. Write each of the following fractions as equivalent fractions with rational denominators. Express all fractions in simplest form. All right. Now, there's more than one way to do this, but here's the basic way every time. I look at this fraction, 1 over the square root of 3, and what I do is I'm simply going to multiply the numerator and the denominator by whatever square root is sitting in the denominator. All right? As long as I multiply the top and the bottom of a fraction by the same number, I'm actually multiplying the overall fraction by the number 1, because any number divided by itself, even if it's an irrational number, any number divided by itself, except for the number 0, any number divided by itself is equal to 1. Now, when I do that, what happens is I get 1 times the square root of 3 in the numerator, which is just the square root of 3, and square root of 3 times the square root of 3 in the denominator, which is just 3, and I'm done. Now, side note, it might be tempting to then say, well, I'll do 3 divided by 3 and just get the square root of 1. Never take a number that is outside of a square root and multiply it or divide it into a number that's inside of a square root. Never do that. Never, 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 never. Okay? But very, very similar. Let's do letter B. Or actually, pause the video now and you try letter B, and then we'll revisit it. All right, letter B is almost identical to letter A. I'm going to start by multiplying the top and the bottom of this fraction by the square root of 2. In the top, the best I can do is leave it as 7 times the square root of 2. And then the bottom, I have square root of 2 times square root of 2, which is just 2. Now again, you might say, I don't think that fraction looks any more simple than that fraction. Now, maybe even looks a little more complicated. And again, I would agree with you if you think that. All right, now let's look at one that takes a little bit more work. 5 divided by the square root of 10, right? And the only reason that this one takes a little bit more work is because if I multiply by the square root of 10 divided by the square root of 10, I'll get 5 times the square root of 10, all divided by 10. And that's great, right? That's where we stopped in problem letter A and problem B, right? But now, the 5 and the 10 will simplify and reduce down to the square root of 10 divided by 2, right? Numbers that are outside of the square roots, those can interact with each other. So in other words, I can divide both the 5 and the 10 by the number 5, this 5, that 10, and I'll get root 10 over 2. I'm literally reducing the fraction 5/10 into the fraction 1/2. I could write the 1 up here, but then it would just be 1 times the square root of 10, which would be the square root of 10. Try something very similar in letter D. Pause the video now. All right, so in letter D, right, I have 6 divided by the square root of 14. I would start that problem by multiplying by the square root of 14 divided by the square root of 14. Whoops, how about that be a 14? We'll get 6 times the square root of 14 all over 14, right? I then look at the 6 and the 14, right? The 6 and the 14, both of those are divisible by the number 2. So if I divide a common factor of 2 out from both of those, in the top I'll get 3 times the square root of 14, in the bottom I'll get 7. So I'll get 3 square root of 14 all over 7. All right, now all of that is simple enough, right? But there are some that are a little bit more complicated as well. Let's take a look at letter E, where we have negative 24 divided by the square root of 8. Now the negative is not really a big deal, and we should certainly consider starting this problem the way we did the other one. Multiply by the square root of 8 divided by the square root of 8. Now when I do that, I would get negative 24 times the square root of 8 all over 8. Okay? And I could say, well, all right, but 24 and 8, right, I could do this, all right, divide out an 8 from both of those, and I'd get negative 3 times the square root of 8. Now, I love that answer, negative 3 times the square root of 8. And I wish I could tell you that we were done at this point. But the problem is the square root of 8 itself can be simplified, right? Because there's a perfect square that sits inside of it. So I could keep going on this one, and I really need to keep going, and write it as negative 3 times the square root of 4 times the square root of 2. That would be negative 3 times 2 times the square root of 2, and that's negative 6 times the square root of 2. Whew. That's a lot of work. And it's a lot of work, let me put a little decimal here, not a decimal, but the multiplication dot, make that a little bit bigger. It's a lot of work for 2 reasons. One, because the 8 and the 24 can simplify at this point, and because the square root of 8 itself can simplify. Now, we're not going to have to worry about that simplifying of a square root either here or here, because the square root of 6, there's no way to simplify that, and the square root of 5, no way to simplify that. But we will run into the same issue over here with the square root of 12. All right, take a moment now, pause the video, and see if you can rationalize and simplify each one of those fractions. Pause the video now. All right, at least the way that we start them tends to be the same each time, right? If I do square root of 6 here, we'll get 15 times the square root of 6 all over 6. Now I should look at those 2 numbers that are outside the square root. They both are divisible by 3, so I need to simplify them by dividing both by 3. And I'll get 5 times the square root of 6 over 2. Problem G, very similar. Start by multiplying by square root of 5 over square root of 5. The numerator will be 20 times the square root of 5. The denominator will just be 5. And now I can divide a 5 into 24 times, and we just get 4 times the square root of 5. Letter H, as I mentioned, is going to be a little bit of a beast, very similar to letter E. I'm going to multiply by the square root of 12 divided by the square root of 12. It's going to give me 3, weird random red, come on negative, negative 3 times the square root of 12 all over 12. Now I can divide that 3 out here, and that'll leave me with a 4. And again, I wish that was it, but I can simplify the square root of 12 as negative square root of 4 times square root of 3 all over 4. This is about as big of a beast as you can get on one of these problems. I need more room, in fact, even on the page. Sorry about that. That's going to be negative 2 times the square root of 3 all over 4. And now I can simplify those by dividing out a 2 in both cases. And I'll get negative square root of 3 divided by 2. Wow. That took a while, right? There was a square root I had to simplify. I had to simplify a fraction twice. You know, first when I divided a common factor of 3 out here, then when I divided out a common factor of 2 out there. So a lot of work there. All right, rationalizing denominators, getting rid of square roots that show up in denominators. All right, now adding and subtracting square roots. In rare circumstances, and I really want to point this out. In rare circumstances, you can add or subtract square roots. The process is very similar to combining like terms. So let's take a look in exercise number 5. Right? Simplify each of the following expressions. Now, what's interesting is that for A, B, and C, there's no square roots at all. I've got 3x plus 5x. I've got 8y minus 2y. I've got 9t plus 2t minus 6t. All of these first things you should have been able to do as early as 6th grade algebra. So I'd like you to pause the video right now and simplify letter A, letter B, and letter C. Go ahead and do that. All right, well, if I have 3 oranges plus 5 oranges, I have 8 oranges. If I have 3x plus 5x, I have 8x. All right, end of story, and it really is that simple. Now, I do want to mention, of course, that the reason that this works, and we talked about this earlier this year, is that what I'm really doing is I'm factoring an x out, and I'm getting x times 3 plus 5, which is x times 8, which is 8x. But at this point in your mathematical career, you should feel pretty confident in saying 3x plus 5x is 8x. End of story. Now, of course, 8y minus 2y, well, if I have 8 oranges and I subtract 2 oranges, I have 6 oranges. And likewise, 9t plus 2t minus 6t, right? If I have 9 students plus 2 students minus 6 students, I'm going to have 11t minus 6t, and that's going to be 5t. I'm literally keeping track of how many x's I have, how many y's I have, how many t's I have. Now, what is 3 root 2 plus 5 root 2? Well, if I have 3 oranges and I add 5 oranges, I have 8 oranges. If I have 3 root 2's plus 5 root 2's, I have 8 root 2's. That's what I have. That's it. Now again, the reason that this works that way is because really what I have is I have root 2 times 3 plus 5, right? I can use the distributive property to factor that root 2 out. That's what I can do. Then of course I can add these coefficients because that's what they really are, right? The 3 is the coefficient on 3 root 2. 5 is the coefficient of 5 root 2. I can add those two together and I get 8 root 2. But really what I'm doing is keeping track of how many of these square roots of 2 that I have. If I have 3 square roots of 2 and 5 square roots of 2, then when I add them together, I get 8 square roots of 2. It's that simple. So see what you get when you have 8 root 5 minus 2 root 5 and 9 root 3 plus 2 root 3 minus 6 root 3. And if you're confused at all, I would look at the problem that's directly above them. Pause the video now and go ahead. Well, in letter E, I'm just keeping track of how many square roots of 5 I have. If I've got 8 of them and I subtract 2 of them, then I must have 6 of them. Likewise, here I'm keeping track of how many root 3's I have. If I have 9 plus 2 of them, I get 11 of them. And then I'm going to subtract off 6 of them. So at the end of it all, I have 5 root 3's. Okay, so what's the moral of the story here? We can only, actually let me advance it, right? We can only add and subtract quantities with square roots that have the same radicand i.e. the same number underneath the square root. Now sometimes we may need to simplify a square root in order to add or subtract, okay? But what we can never do is add or subtract square roots if the numbers underneath them aren't the same or if we can't make them the same. So let's take a look at exercise 6. Letter A, square root of 8 plus 5 times the square root of 2. So at first glance, there's really nothing we can do with this because the 8 here and the 2 here don't match. And we certainly can't say it's like 6 times the square root of 10. We can never add the two numbers underneath the radical. Ever. Okay? So the square root of 2 plus the square root of 2 is not the square root of 4. Ever. All right. But what I can do is I can say, well, the square root of 8 can be simplified, right? It's the square root of 4 times the square root of 2, which is 2 times the square root of 2, right? That's just simplifying the square root of 8. So this now becomes 2 times the square root of 2 plus 5 times the square root of 2. Now, because these two match, right? Because these two are the same, or they match, I can now say that's 7 times the square root of 2. All right, but they must match each other. All right, play around with letter B and letter C, see what you get, and then we'll go through them. All right, again, in letter B, I have 2 times the square root of 27 minus the square root of 3. One thing I certainly can't do is do 27 minus 3, get 24, and somehow play around with that. I've got to have the same numbers underneath here. Now, there's nothing I can do to the square root of 3. Nothing at all. But I can do something with the square root of 27, right? I can write that, don't lose the 2, as the square root of 9 times the square root of 3. Now I'm going to have this minus square root of 3. This I can then make into 2 times 3 times the square root of 3. Let's still not lose that. And then I've got 6 times the square root of 3 minus the square root of 3. We'll finish this off now in a moment, right? So in other words, I've taken 2 times the square root of 27 and I've made it into 6 times the square root of 3. That's all I've really done so far. And if I have 6 oranges minus 1 orange, I have 5 oranges here. If I have 6 times square root of 3 minus square root of 3, I have 5 square root of 3. All right. This one's really crazy, right? Square root of 20 plus 9 times the square root of 5 minus the square root of 45. Nothing I can do with the 9 times square root of 5, that's done. Certainly I can't take the square root of 9 because it's not underneath the square root, so don't go there, right? But what I can do is I can take that square root of 20 and make it into root 4 times root 5, and I'll simplify that in a moment, plus 9 times square root of 5. The 45 I can break into the square root of 9 times the square root of 5. And by the way, before I even move on and do anything more, notice I've got a square root of 5, a square root of 5, and a square root of 5. So I'm getting there, right? I'm getting there. So what will I now have? I'll have 2 times the square root of 5 plus 9 times the square root of 5 minus 3 times the square root of 5. And that will give me 11 times the square root of 5 minus 3 times the square root of 5, and that's 8 times the square root of 5. Again, I can only combine square root quantities when they have the same radicand, when they have the same number under the square root symbol. All right, let's wrap this up. Now today we were tasked with learning a little bit of the arithmetic of square roots, and really that boiled down to 2 new things. One thing was rationalizing the denominator. And we do that by multiplying a fraction that has a square root in its denominator by the number 1 creatively, right? The other thing we looked at was how we add quantities that have square roots involved in them. And we saw that the only way we can do that is if those square roots have the same number underneath them. And then it's just like combining like terms. It literally is, but you kind of treat the square root of 2 or the square root of 3 or the square root of 5 or whatever as like an x or a y or a z or something to that effect. All right, well, we'll be doing more square root arithmetic as we transition back into algebra because that square root arithmetic will show up in the algebra that we do. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking, and keep solving problems.